Here, that was Raymond E. Cajal at the kitchen table, his drawings, detectors, single point detectors, cameras, and I'm going to talk about software. So first, these single point detectors. So basically, in all these detectors, what's happening is that we start with a photon. Photon, through the photoelectric effect, is converted somehow in an electron, a charge, and then to read out that charge, invariably, we measure a voltage, and that voltage is then converted in a digital number using a so-called AD, analog digital converter. And that digital number arrives in the computer, and then we hope that a digital number has a relation to that photon in the beginning and the number of photons. Now, if we have a single point detector, basically what happens is that we're scanning a single point, a single beam of light over the image. We're measuring photons at minuscule little time points. And then we have some kind of electronics to relate the movement of that beam to a time point, the time that we measured the number of photons, so that we can then place them back again on a virtual image so that reflects what we saw there initially. But you need to correlate time with XY position, and you need to read this thing out fast. And you can see, like, if we have an image with, I don't know, 1 million positions, that, if you do that at 1 megahertz, which is pretty fast, that you still only get 1 image per second. So that's pretty slow. And so that's one of the issues with confocal microscopy, where you use these single point detectors. And so the alternative is to measure out the whole image in one go. So to project it using a lens on a camera. So, and then your camera is built so that it can measure out all these little cells that we often call pixels at one and the same time. So, but in the end, it's kind of the same thing. Photons become electrons, and those are then transferred through that ADC converter into a digital number into the computer. Now, so first, these single point detectors. The kind of archetypical one is the so-called photomultiplier tube, the PMT. In a PMT, we have a photocathode, and that photocathode is the material that that absorbs a photon and through the photoelectric effect changes it into an electron. That electron is then amplified through a voltage differential onto a dynode. Those voltage differentials are set up so that it goes from dynode to dynode, and at each dynode it elicits more electrons, and so they're basically accelerated. The energy increases, that then creates in the end a big cloud of electrons, and that big cloud of electrons is then being read out, transferred into a voltage, and then eventually into a digital number. So photomultiplier tubes are very useful. They're linear, high gain, fast response, but they have a relatively poor quantum efficiency. And so that poor quantum efficiency means that we only collect, almost 1 out of 4 photons on that photocathode, which is not great. They can be run in photon counting mode so that you count pulses. So when you do that, they have no background whatsoever, because you set kind of a threshold above which you count it as a pulse and below which you don't. But that way they're much slower. Or they can be run in linear mode and then measure current, and they're much faster then, but also noisier. There are many variations of these PMTs. The cathode material can be changed. To be honest, the current confocal, I have not myself worked with confocal microscopes for a long time. I will be working with one again soon. And I'm kind of looking forward to learning more about the current state of all these detectors. But this is one of the basic technologies, and I encourage you all to ask your confocal rep to explain you more about what exactly is the technology in the current detectors. I asked ours, and he didn't get back to me, so um, I'll tackle him whenever I can. So the other major technology are these so-called avalanche photodiodes, or APDs. So APDs are based on semiconductor technology made of silicon, which is also the same stuff that goes in solar cells. So this material is very good at absorbing photons and changing them into electrons. And this is also the same stuff that underlies the cameras that we will be talking about. In an avalanche photodiode, the electrons that are captured are being accelerated through this depletion region by setting up a voltage differential. They slam into the second layer, and they, through a process called impact ionization, they then elicit more electrons. So they're basically amplified in this solid state material. They have a high quantum efficiency because of that the photocathode material, and they can be used to count single photons, in which case they're called SPADs, for single photon APDs. They can look like this, or there are probably other designs as well. And you will encounter these quite a bit in current, but they can overheat if they run too fast. So certain precautions have to be taken that not too much light hits them. And so there are, even automated circuits to shut them down if too much light hits them, etc. Now, kind of a new technology which breaks through this barrier between fast single point detectors and slower but many point detectors are these SPAD arrays, which are super interesting. So basically they are one or two dimensional arrays of these SPADs, so that they can, in a small area, detect multiple sites simultaneously. So these can work very, very fast. This is all still more or less technology in development. I actually talked to someone who works in a biophysics lab who is actually designing these things themselves. It's super interesting because it's kind of like, you literally on like Illustrator, like software, draw these things up. And if you have a connection at a fab, they can manufacture them for you. And this is all still kind of doable as long as you have the right connections, which is super interesting. And one of the examples, commercial examples that I'm aware of an array like this, they don't call it SPAD array, so I'm not totally sure what they have, but it's this Zeiss Airiscan, where they, instead of having a pinhole in their confocal, measure a small surface and use this to do all kinds of quantifications, and also to actually improve the spatial resolution of their microscope. All right, so on to cameras. So they can look like this. An old Hamamatsu Orca camera, and an Endor Neo CMOS. In the end, they all have like what you kind of see here, which is kind of the same that you have in your cell phone. There is a two-dimensional array of, probably about 1 million here photosensitive areas. So how do these things work? So on these sensors, there are things that very much look like the avalanche photodiode, except there's no amplification that is happening. So there is a silicon dioxide layer that absorbs incoming photons through the photoelectric effect that becomes an electron, They're then held in a potential well until you decide to read out the chip, and that can happen in different ways. And then that charge that is sitting there will be changed into a readout as a voltage, and that voltage will be transferred into a digital number that goes to your computer, and that can then again be related to the spatial element of your chip, so that you get, like in your computer, a reflection of what that chip saw. There are two basic types of architecture. So there are these CCDs that are more or less passive. They have that potential well, and that's it. And then there are the CMOS types detectors that have a potential well, but they also have a bunch of electronics around it. So they have a couple of transistors so that they can actually do that change. They can do some amplification right there. They can reset, empty out the chip right here, the pixel right here. There's electronics around it. You also immediately see, well, that electronics around it is going to absorb light, and to defeat, to help with that, there's a micro lens that will direct all the light on the photosensitive area. Now, a decade ago or so, we wouldn't even talk about this because the CMOS sensors were very noisy. The technology have improved so much that we now solely, almost only have this CMOS technology. So this has gotten so good that most of the cameras you guys will be buying or working with will likely be of this CMOS type. Just for historical perspective and still have a bit of an idea, CCDs are passive. They can move charge over the whole chip. And one interesting way of explaining how that works is with this bucket brigade. So the pixels are buckets that collect rainwater while it's raining. Then it stops raining, and then we start to read out how much water fell in each of these buckets. They are moved one row at a time into this serial bucket. Then the serial bucket is being moved one by one into this measuring container, the readout node. And here you measure how much liquid there was in each bucket. And if you do your bookkeeping right, you know then to which pixel that correlated to begin with. So CCDs, all the charge goes through one and the same readout node. And that readout node has to be pretty fast. And you can also kind of see, like, if you read out fast, you're going to make more errors and you're going to have more noise than when you read out more slowly. And that's exactly the case. So you can run these readouts at different speeds, 1 megahertz, 10 megahertz, 20 megahertz, and you will see that you get different noise characteristics with different readout speeds. Now, to give you a little bit of an idea of how this really works, is that every pixel has like 3 lanes of electrodes. These electrodes are clocked differentially, so that the one in the middle is on to collect the electrons under this electrode. And then once you start readout, you switch that one off, you activate the one here to move the electrodes there, and you continue clocking to clock the charge over the whole chip into that serial register. So it's all like, super cool technology, at least as far as I'm concerned. Binning is accomplished on CCDs by clocking into the serial shift register twice. So to collect the charge of 2 of these pixels into 1, and then clocking the serial shift register twice into the readout node, so that you now have all the charge of these 4 pixels in one readout node. And so you, since that readout is the rate limiting factor, you can speed up the readout. You also get more charge per pixel, so you and you have only one contribution of readout noise, so you increase your signal noise resolution. Um, but of course, you give up spatial resolution because that charge you measured now comes from this area of 4 pixels rather than 1. Um, Now, I told you in that bucket brigade example, like, okay, it now stops raining. Well, how do you stop the light from actually reaching your sensor? So in old sensors, what happened was that there's actually a shutter that you put in front, and then you start the readout. Well, that's of course a bit of a pain because those shutters are slow. It takes like tens of milliseconds to fully shutter. They cause a lot of vibrations. But those are these full frame cameras. They need some kind of shutter before you can start readout. Uh, then another strategy was to double the chip and have only half of it photosensitive. So the other half you make completely opaque. You put like a shield in front of it. And then you can very quickly move the content of what you exposed here into the second half of the register. There can be a little bit of smearing because there's still light hitting that while this happens, but it's so fast that it's very minimal. And then, at ease, you can read out the chip while it is sitting here. So this frame transfer methodology is often used in EM, is almost always used in EM CCDs that I will also explain. And another technology is to use these micro lenses that we already talked about. So then half of the chip is, and that's interspersed, is opaque, and the other half is photoactive. And you put a micro lens on front of each of these two so that you direct as much light as you can to the photoactive part, and then can transfer very quickly into the opaque part and then do your readout. And those are called interline transfer CCDs. Um, so color cameras. So what happens in color cameras is that each of the pixels themselves have a color mask, often a so-called Bayer mask, where you have like 2 green pixels, a blue and a red one to kind of match the photosensitivity of our eyes. And we don't like using those for fluorescence. And the reason for that is that the filters that we can put in a microscope are way better than these Bayer masks. Plus, when we have these filters here, we are throwing away a lot of the light because, blue light hitting that green pixel will not be detected. The red light will only be detected by one of these pixels. So, there's just a huge amount of light loss. And what you also should realize is that, the software is actually interpolating from its neighbors the content, the blue, red, blue, and green content of each of these pixels. It's not a direct measurement, but it's just an estimate based on what the neighbors detect. So also your spatial sensitivity goes down. So, having said that, hey, often these, even a cell phone camera that has this Bayer mask, sometimes you can do cool stuff with it. So just understand how it works, but don't be inhibited to use any of these things. A lot of numbers with cameras you can easily find online, and they are relatively telling. So first of all, every camera you want to know how many pixels they have and how big they are. And so often these data sheets will tell you these things. So this camera has 1344 by 1024 pixels. They are 6.45 microns square in size. You want to know the quantum efficiency, which fraction of photons that hit the CCD is actually converted into an electron. Full well capacity, like how many pixels can one well contain before it overflows, can no longer see them. Very important factor is the read noise. If no light hits the detector and I read out every point, what is the noise that the camera itself adds? The dark current, when I expose with for a long period of time in absolute darkness, what kind of background do I get then? So this is it differs from the read noise because it's integrated over longer periods of time. So often cooling can reduce that dark current. To be honest, this is almost more important for when you want to do really long exposures. And we often nowadays want to go fast. Readout time, how quickly can the camera be read out? So what is your, in a way, your shortest time before you can collect the next image? And then something called the electron conversion factor. So when I get my digital number out from this camera, how many photons actually were there at that pixel? And there are ways of measuring that yourself, but you can also ask your manufacturer to tell you what that number is. Now, so some thoughts about magnification and pixel size. Often I think about projecting the chip into the sample plane, and then, what is the size over there? So if we have here a camera with 6.45 micron squared pixels, and I use a total magnification of 100x to the object, then each of these pixels is collecting light roughly from an area about 65 nanometers square. So when I project my sensor onto my sample, it would be 65 nanometers per pixel. And I don't know, to me, that is kind of the, insightful number and a number you always want to be aware of. Now, how big should that number be? So, it's very clear that if you start out with too few pixels, it all gets very blocky. And then you add more pixels, it starts looking better. But at a certain point, it stops looking any better. So what is the optimum here? So how many pixels do I need? And, you probably have talked before about optical resolution. So this, of course, depends on optical resolution, but then also on how to sample optical resolution. And, there's a theory from signal processing world, the so-called Nyquist Shannon sampling theorem. And that states that you need to have at least 2 pixels per resolvable element, where 2.5 to 3 is preferable. And so you can kind of imagine or get a feel for that. If you have 2 points that you can discriminate, you would want like 3 so that you get like 1 in between where the signal, where you actually see a dip so that you know that there are 2 points here. So 2 to 3 pixels per resolvable element. Now, what is the resolvable element? And you must have talked about that, there are various criteria. One of them here is the Rayleigh criteria. It depends only on the numerical aperture of the objective, the angles that your objective can collect, and then is roughly 0.6 times the wavelength of the light divided by the numerical aperture. And for something like green light, that comes out to something like roughly 220 nanometers. So the 220 nanometers must cover 2 pixels. And the easiest to think about is what magnification do I need to get my pixel size down to 110 nanometers. So the pixels are 6.45 microns. We want them to be 110 nanometers, 0.11 microns. And when you divide these two numbers, it gives you about 60x. So a 60x lens would be perfect here without any intermediate magnification. With a 40x lens, you wouldn't you would lose some spatial resolution. Although I found that undersampling is often fine. People really like a larger field of view more often than getting full resolution. 60x you would sample completely. 100x you would be oversampling, so you would get a smaller image and you would smearing out your resolution over too many pixels. Although you would get like the a slightly better, you would be separating your discernible elements into 3 pixels rather than 2. Quantum efficiency. So, what I often forget about and want to stress here is that quantum efficiency is wavelength dependent. So these cameras are often, most sensitive in the green. You really want to match this also with where you're looking. So if you're looking at things like Sci-5, you see that both these cameras start to give in a little bit here in the IR. That fpbase.org that I talked about includes quantum efficiency curves of the camera, so it takes all that into account. But you see here this difference between front illuminated and back illuminated, and back illuminated clearly looks a lot better than that front illuminated. So what is this difference here? Now, so we talked about it, that these CCDs have all these electrons in front of them. They are semi-transparent. The CMOS also has a lot of stuff on front here. All of that absorbs light and it scatters light, so it lowers the amount of light that can actually reach the photoactive layer. So what the designers thought at one point, hey, we have the whole back of this thing. If we etch that out, so back thin it, then we can invert the sensor and we can now have the light reach it without anything in between and increase the quantum efficiency. And this works. It works with CCDs. It works with CMOSs. It makes it more complicated to fabricate these, and it makes them more fragile. They break more. Cost goes up, but it definitely is advantageous from points of getting more sensitivity, getting higher quantum efficiency. Now, we all know that when you expose longer, your image starts to look better. So why is that? And possibly again, like, how long is good enough? Now, the first source of noise is given by physics and is a type of noise that is unavoidable. To be honest, when I started this, what I thought is like, if you have a light source, that light source gives out photons. I know photons are kind of like particles or also waves, but you can think of them as little bullets. And I thought, okay, these all come in nicely and regularly. So if you sample at a small time interval, you know exactly how much there were also over longer time intervals. Well, that appears to be completely wrong. So that is not how nature works. Those photons are not like a nice regular stream. They come out in a stochastic manner. They are it is like in a way it's like radioactivity. It's kind of like a stochastic process, and those photons are actually Poisson distributed. So when you measure at a small time interval, you don't exactly have a good measure for the photon flux, how much this is giving out per unit of time. You're just sampling, and if you would sample longer, your estimate would improve. And so it turns out that that Poisson statistics dictates that photon shot noise goes with the square root of the flux. And that means that if you expose 4 times longer, your estimate gets the square root of 4 is 2 times better. And so this is unavoidable. This is given by physics. Nothing we can do about it. Now, the other sources of noise, there are things we can do about it. So those are introduced by your detector, be it a PMT or a camera. One of them is that read noise. Already talked about it. The faster, the noisier. It's independent of how many photons were in your pixel. It's kind of added every time. The dark current, you can cool to lower it, but since we're going fast, we often don't care about it too much, so not too important. Then fixed pattern noise, and that one is actually more important than we realize. The problem is it's very hard to measure. So it is caused by not all pixels responding equally. And the way to really measure that well would be to provide a very even image that provides the same amount of light everywhere, which regretfully is kind of hard. I have some tricks of doing it. And often what we do is use this process called flat fielding. So we take one such an image and then normalize with that flat image to correct for this fixed pattern noise. So its contribution is also maybe less important. So the most important one is that read noise. Now, when you think about it, so our signal is a number of photons, a given number of photons per unit time, photon flux. The noise is now the square root of that number of photons, the photon shot noise, plus the read noise, so the square root of the read noise squared. So what this means is when the number of photons reaching your detector is smaller than the read noise squared, then read noise is your big problem. And when the number of photons is greater than the read noise squared, then that shot noise is the problem. And you cannot do better than that. So that is where you want to be. So you want that read noise to be as small as possible. And that is often, for me, one of the first things I look at, like, okay, does this camera have a low read noise? Here we already talked about this. When you want to double your signal over noise, you need to, and you only have shot noise, you need to expose 4 times as long. So you see that's kind of painful. In the end, there's no limit to the longer you can expose, the higher your signal noise becomes. You will have to decide, okay, this is good enough for me. You're never going to defeat that photon shot noise. Kurt Thorne made these nice demonstration images where in this image we have on average 10 photons per pixel hitting the sensor. And he then added photon shot noise. So, stochastically added the square root of the intensity at each pixel here. You see, you already get quite a noisy image, but it's still, you can quite well see what came from where. But then when you add 5 electron read noise, the image degrades quite a bit, and you start totally losing some of these finer microtubules in this case. You can no longer tell where they came from. Again, to show that, that read noise, you want to deal with that. Now, the middle, so I don't know, around 2000, 2005, this technology came up to lower the read noise of CCDs, and it was these electron multiplication CCDs. And I'm telling you this because you still may encounter them. We still have quite a few in the lab. They are these frame transfer CCDs, sensitive here, transfer in one go to this area, and then transfer into this extended multiplication register. And what happens here is that each bucket, each package of charge is clocked into the next pixel under relatively high voltage. And then just like in these APDs, you get an amplification through impact ionization. So you can regulate the voltage differential between these. and regulate how much amplification you get. But you can imagine that if you do this in 500 steps, even a very small amplification of like 2% in each step will give you a very high amplification at the end. And so you're now amplifying your charge before you get to the readout node. And then even though the readout node has a certain readout noise, you get so much more input is that readout noise become negligible. And so these EM-CCDs were really a nice strategy to run cameras faster and have still relatively low effective readout noise. Now, we are currently almost completely switching to these CMOS type devices. And that is because the manufacturers somehow have figured out how to lower the read noise. I don't exactly know what the advances were here. I always feel like they keep things secret from us until they can sell us the next generation of what is really cool. But you literally can buy cameras now that have less than an electron read noise, at least in certain modes. And remember that noise contribution goes with the square, and the square of less than 1 is even less than 1. So less than 1 is, there you're really fine. The cool thing is also that these cameras can be much bigger than what we were used to with CCDs. So you can get a larger field of view, and they can run super fast, some of them even in the kilohertz range. So there's all kinds of cool stuff you can do with them. They often will have these micro lenses, although there are also back-thinned versions of them now. In the beginning, they all had fixed pattern noise type things, but they also have figured out to do how to deal with that. One interesting thing to pay attention to is that they can have this global shutter, so they're not exposing in one go, but kind of in a wave that go over the chip. And you can search online for cool explanations how if you image something that moves fast, like a propeller of an airplane, you get all kinds of very bizarre artifacts of this global shutter, of the rolling shutter rather than the global shutter. So in general, if possible, you will want to use global shutter. But in many cases, you can also get away with that rolling shutter readout. Now, so how these things often work, again, so here is this is kind of an interline setup. Not, totally sure if this would be valid for some of them. So you would have a micro lens that projects the light onto the photosensitive area. These are set up that they have their own little amplifier built into the chip itself, also something that can reset. They still transfer the charge along one column and then get to the final readout amplifier and AD converter. And that will then, so there are now many AD converters. That brings with it a problem of making all these AD converters for all these columns exactly the same. So you could have column artifacts, these types of cameras. And then often these digital numbers go to a little computer that is built into the camera. It's called often a field programmable gated array, something that can be programmed in the camera and be very dedicated to very fast processing. So you should be aware that these newer CMOSs do a lot of massaging of the raw data already before they send it to you, which can be a little bit disturbing. But as long as we can trust the manufacturers to do the right thing, it also can lead to really great characteristics. Now, one general question is, how many intensity levels can you distinguish in a camera? And so when you think about it, it's given by the full well capacity, how many electrons can be held in one pixel, divided by the readout noise. The readout noise is kind of the one step that you can discriminate going from one. If the difference is less than the readout noise, you don't know if it's the same. But if it's more, then you know, okay, these things are different. And so in this example, that would lead to a 3,200 different grayscale levels. It's a little optimistic probably. So often, people use 90% of the full well capacity divided by 3 times the readout noise, but it's probably pretty good, like 960. And so if you read up on human physiology, like an eye with a fixed iris, so we don't go in accommodating, but just at a given intensity of light, the human eye apparently can only discriminate about 100 grayscale levels. So a camera is pretty good. And so this is different from how many bits your camera delivers. So this is what happens analog, what is the physical thing, and then your AD converter is kind of sampling this. So what you want to be sure of, like these 960, you want this camera to be sampled at least with 12 bits so that you sample it with 4096 grayscale levels, because that number has to be higher than this one, and otherwise you have loss of data. I hope that's clear, but it does mean, you often see 12-bit cameras or even 16-bit cameras with like 65,000 grayscale levels. And if you have only 8 bits, that means that camera is very poor or you're super undersampling it. Although sometimes you may want it because that is good enough for what you're doing. Now, to look at an image, our computer screens only display 8 bits, so 0 to 255. So we have to map, our 12-bit image, in this case, 4096 grayscale values, onto that 8-bit screen. And so the normal way to do that would be to just do that linearly, but don't forget, we are like putting a whole bin of things where we can tell the difference in grayscale value, but we all put them in the same bin, so we are losing information here. And so setting contrast and brightness changes that relationship, and it's a totally fair thing to do, especially with something like a 12 or 16-bit image. If with a linear scale, you cannot see all the information that your camera actually delivers to you. And so playing with brightness and contrast lets you see things in the data that is there and that is real, but that your screen does not let you see. Now also, these two images here look very similar. So they have been auto-scaled, but this image was actually exposed much less than this image of the diatom. And when you look at the histogram, so the histogram is a plot of the intensity values on the x-axis and the number of pixels with that intensity on the y-axis. And so that histogram, when you're acquiring data, is your friend. And that's something you want to be looking at. And in general, you want to maximize your histogram. You do not want to have saturated values that clip, because you don't get information there. But on the other hand, unless there are other things at play, you want that your data to fill that histogram as much as possible. So the image on the bottom, even though it looks the same, the histogram is way narrower, and the amount of information and the amount of processing you can do with that image is much less than the image of the top. So always, keep an eye on your histogram, always have it available when you're doing imaging, because it tells you something about the information density of your image. Now that feeds into computer control of microscopes. So microscopes have these detectors that in the end are coupled to the computer, and the computer needs to read them out and create the image. There are also things like shutters, there are stages that move around. Microscopes are kind of robotic instruments these days, and to do more or less anything with them, you need software that tells your computer to do things in a specific sequence and the way you like that all to be done. Computers have different interfaces to devices. One of the old ones that still is widely used is the serial interface. It's very simple. We only use like 3 pins of this. There is a pin to send data, a pin to receive data, and a ground. It goes through this cable to the device. You agree on a certain speed with which you're going to send data, which is called baud rate, and there you go. And so don't need drivers or anything. That's all built in the operating system of every computer. So, and therefore it's still a very popular interface. There are even USB to serial converters so that you can still use those devices. Often that is even built into a device that has a USB interface. And to be honest, everyone still likes those things, although they were supposed to be replaced by USB like 25 years ago. So USB is kind of a faster version of this. Also has a few more data lines, but it's kind of similar. But USB needs drivers. So to talk to a device, you now need a driver. You need to write that driver for every operating system. So it's more kind of like a software hurdle that's in the way. Nevertheless, USB 2, USB 3 can go much faster. And so there are even now cameras that with USB 3 can go at pretty decent speeds. Nevertheless, cameras still will often have their own kind of card, and those interfaces are either things like camera link, or we're now seeing coax that sends the data over one cable with only one data and ground. Different kind of interfaces, but in the end, what these things do is pump data into your computer. You will need a driver that knows how to talk to it so that you can get that data into your software. So that's how you connect your computer to the outside world. And then you need software that knows how to talk to all these different drivers and make things go. And yeah, here I'm kind of putting a plug-in for our own software, which is called Micromanager, which is open source. It has like a pluggable interface so that it can work with many, many different components. And it has an interface that runs under as a plugin in ImageJ, so that people who don't know anything about programming or whatnot can use it with most types of microscopes. It works best with cameras. There's little support for scanning systems. Confocal microscopes almost always come with their own software to begin with, and the vendors don't open that up. We started that now almost more than 15 years ago. Single interface for all microscopes, so it works the same on a Zeiss, Leica, Nikon, Olympus microscope. Has a pluggable interface. Lots of people, including many companies, have contributed code to make their equipment work with it. I'd say it's pretty good. And when something doesn't work, I fix it. And we in our lab are using it all the time ourselves also, because it lets us do a lot of things that would be impossible with commercial software. And then it is free. So it's just a free download away from micromanager.org. And there you go. So to be honest, quite a few people use it because it doesn't cost them anything. Whole lot more stuff, just saying that it does a full multi-dimensional acquisition, time-lapse, Z-series, multi-channel, multi-position. Works with a lot of things. It works on many different operating systems. You can script it. Recently, and it will soon be out in Nature Methods, Henry Pinkert designed a Python interface so that you can write full Python scripts to work with all the Micromanager code, and it's free. Go to micromanager.org for more information. There are many people using it. And there's a lot of evidence that that's really the case, including this forum here, image.sc, where I now get daily a couple of support requests, and part of my daily routine is to answer those in the morning and help people. And I think that's where I'm gonna leave it. Again, need to thank Kurt. Some things came from, I don't know if this micromagnet is still up. The James Pauly book of biological confocal microscopy. Jane Sick wrote all these cool things about photon transfer curves and CCDs, and has a lot of information about CCDs. I actually have scripts to measure the photon conversion factor if anyone is interested in it. But in the interest of time, I certainly want to leave it here.